What is the purpose of studying world of discrete mathematics? When there are multiple circles drawn all over a piece of paper, it would be difficult to just glance at it and tell how many there are. Even if we were to point a finger to each and count, it is just as confusing. How could we count the number of circles quickly and accurately? This can be easily done by attaching a numeral to each circle. If we attach one number at a time to each circle starting with 1, we would not miss a circle or count one circle twice. As such, numbers are a tool to help us count the non-continuous, separated, discrete world. Numbers play an important role in helping us comprehend the world we live in at a glance and come to a new understanding of it. The continuous and the discrete coexist in nature. The continuous means that it does not stop and continue to extend. The discrete means that each thing is separate, and we may count them. For example, time and space are continuous, while the number of leaves and people are discrete. Although continuous objects seem static and motionless, it is really going through endless cycles of creation and destruction. This makes it difficult to find regularity within it. However, with discrete objects, if we can express the number of discrete objects as numerals, we can easily figure out their characteristics and regularities. To study something mathematically, we must be able to draw the object. Careful observation must take place first to draw it properly. Every living thing has a pattern. Patterns are the traces of life and death of a living organism. The specific traces of numerous lives and deaths appear as patterns. In other words, patterns contain the principles of creation and destruction. The purpose of studying mathematics is to figure out the secrets of nature, the secrets of life and death in nature. Through mathematics, we can create a program to predict what will happen in nature. However, this process is not necessarily easy. Mathematics also plays an important role as a standard in the process of figuring out how structures within nature will expand or suddenly begin to shrink and disappear in the world of invisible force and laws. Thus, in order to figure out the secrets in nature, we must draw abstract pictures of the patterns we discover through observation. This is the reason why we venture into the world of figures. If a pattern can be expressed as a figure, it can be placed in the world of numbers or characters. Through equations made up of numbers and characters, we can find the regularities within nature much more easily. Prediction programs that discover the secrets of the creation and extinction in nature come about through mathematics. The best mathematical tool that helps us understand the non-continuous discrete world is natural numbers. Natural numbers are also known as Hindu-Arabic numerals. The Hindu-Arabic numerals are named so because Indians invented the system and Arabs spread them to Western Europe. The first traces of Hindu-Arabic numerals were discovered on a stone pillar in India built by Ashoka the Great circa 250 BCE. However, we do not know when and how these numerals spread to Europe. There are records of Arabs who, having conquered parts of Europe and India, invited Indian mathematicians to Baghdad and had them settle there. This tells us Indian mathematics was introduced to Europe through traders or travelers. Once we observe components of nature closely and attach numbers to them, finding the mysterious regularities within nature become much easier. For example, Fibonacci sequence, a series of numbers where each number is the sum of the two previous numbers, is regularity of numbers often found in nature. As regularities in nature reveal itself, we understand why nature takes certain forms and go on to predict how nature will change in the future. Leonardo Fibonacci, a famous Italian mathematician, studied Arabic mathematics while traveling through Egypt, Syria, Greece, and Sicily. He made a significant contribution to the development of European mathematics by introducing what he had learned to the Europeans. His introduction of the Hindu-Arabic numerals to Europe was especially groundbreaking. Fibonacci recorded the following in his book, Liber Abaci, the Book of Calculation. Suppose a farmer raises a pair of newborn rabbits. Starting from the second month, the pair gives birth to a male and female rabbit every month. Every newly born pair of rabbits also gives birth to another pair every month starting from the second month. After a year, how many pair of rabbits does the farmer have? The first pair of rabbits become adults after a month and give birth to another pair on their second month. This pair of rabbits also become adults a month later and give birth to a pair of rabbits every month thereafter. If we count the number of pair of rabbits every month, it becomes 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, etc. With a closer look at the sequence of numbers show that the sum of the two former numbers makes the following number. We call such series of numbers the Fibonacci series or the Fibonacci sequence. After close observation of flowers, which bloom in order to preserve their species, Fibonacci realized that the number of petals follow the Fibonacci sequence. When we count the number of petals on flowers around us, we see that they usually have 3, 5, 8, or 13 petals. When we write out the number of petals in ascending order, it matches the Fibonacci sequence, 3, 5, 8, 13, 21, 34, 55, 89, etc. But why does the number of petals match the numbers in the Fibonacci sequence? Before the flowers are still a bud before they bloom, the petals need to overlap with one another to protect the pistil and stamen inside. This overlap is most efficient when the number of petals is 3, 5, 8, 13, and so on. Let us now take a look at a sunflower and the seeds in its center. We discover clockwise and counterclockwise spirals. Although the number of the spirals going one way and the other vary depending on the size of the flower, the numbers are always neighboring numbers in the Fibonacci sequence, such as 21 spirals going one direction and 34 going the other, or 34 and 55. Sunflowers have a spiral arrangement to fit in as many seeds as possible densely in the small space so that it can withstand rain and wind. These examples show us how even plants are continuously making an effort to survive. If the sunflower seeds did not have two series of spirals and only had spirals going in one direction, much space would have been wasted. The secrets of the Fibonacci sequence hidden within flowers do not stop here. As we divide the number in the back with the number in the front, we arrive at the number 1.618. 1 to 1.618 is the golden ratio. Flowers do not just happen to be beautiful. There is a clear reason why they appear beautiful in our eyes. Flowers contain the perfect ratio that people are the most comfortable and natural. Flowers entice us and grab our attention with their beauty composed of an exquisite and mysterious balance. In order to discover the secrets of nature, we must understand how nature is structured and the world of invisible force and laws within the structure amid repeated creation and extinction. By expressing the discrete world that makes up nature's structure into numbers and characters, we go one step closer to discovering the secrets of nature. What logical reasoning for the Fibonacci sequence in Tower of Hanoi? Nature is the best math textbook that we can have. The ideal math education is a series of training to help learn the secrets of nature. Such mindset helps develop a proper math curriculum. Observation of nature is the first step to ideal math education. Through the observation of nature, we find patterns and apply numbers and characters to each pattern. Through this process, people have been able to find laws of nature that exist between numbers and stepped closer towards the beautiful ratio within nature, the golden ratio. There is a constant ratio in the nature around us and the objects we use in our daily lives. The golden ratio, which we know as being the most harmonious, stable, and the most beautiful, originates from mathematics. The golden ratio became widely known after Greek mathematician Euclid defined it theoretically. The Elements, the first mathematical textbook, written by Euclid, defines the golden ratio as a straight line is said to have been cut in extreme and mean ratio when, as the whole line is to the greater segment, so is the greater to the lesser. The ratio created with Euclid's definition to the third decimal place is 1.618, the golden ratio. The golden ratio is often found in ancient architectural buildings. When we look at the Parthenon in Athens, built in 5th century BCE, the ratio between the height and width of the Parthenon and that between the pillars and roof are 1 to 1.618. The golden ratio can also be found in the pyramids, which are considered one of the greatest architectural marvels. Then, what significance does the golden ratio have in modern architecture? The golden ratio is applied to most facades, the side of a building seen horizontally from the front or the side. The dimensions of a window or the placement of the pillars in a building also often follow the golden ratio. However, because the functions of modern have become much more complex, architectural designs have been shifting its focus on functionality than the golden ratio. The golden ratio can also be found in Venus de Milo, known as a representation of beauty itself. The ratio of the upper body to the lower body divided at the belly button, the ratio of the head from the neck up to the torso from the neck down to the belly button, and the ratio of the legs from the knee down to the knee up to the belly button are all approximately 1 to 1.618. The golden ratio is also an important factor to consider when taking pictures. Composition is one of the standards that determine whether a picture is good or bad. It is important to determining how to put what we see into a frame, and this is where the golden ratio comes in. When we take a picture of a person, we usually place the person at the center of the frame. However, this may result in a picture where the subject does not look natural in the background. In order to solve this problem, the frame is divided into thirds, and a person or background is placed in the rest of the screen to look natural. The golden ratio makes this possible. Most pictures are rectangular, with the sides forming a golden ratio of 1 to 1.618. If we were to divide up such rectangle of a golden ration by 1 to 0.618 endlessly, we get a single point. By applying this idea to the four sides of the rectangle, we can get 4 points from the golden ratio. If we take a picture with the subject at the point, we can get a resulting photograph with a golden ration composition that looks the most natural and harmonious. The golden ratio makes people feel a sense of stability and comfort, which is why it is often used to determine the photographic composition. Beauty is subjective and typically remains within the unquantifiable realm. Still, the golden ratio that appears most aesthetically pleasing to human eyes. The golden ratio is a beautiful ratio found in nature as it is, not something people made up artificially. This ratio is also commonly found in good-looking people. Look closely at the width and length of a person's face or the width of the nose and the forehead. The faces we feel are natural and aesthetically pleasing has the golden ration hidden in them. As such, the golden ratio started as a concept in mathematics, but it is now deeply embedded in our daily lives and has become the standard for beauty, harmony, and balance. Another good example to help us understand the discrete world along with the golden ratio is the legend of the Tower of Hanoi. The Tower of Hanoi was first introduced in a book by Enclosed Siam in 1883. The Tower of Hanoi's problem is introduced in Recreations Mathematiques. In 1884, no later than a year after the publication, Henri de Parville, a French journalist, revealed that the author of the book was Edward Lucas, not Claus. Lucas was a much-renounced mathematician of the time. In his book, he introduced a legend about the Tower of Hanoi that had been passed down by word of mouth, making it widely known. The details of the Tower of Hanoi are as follows. In a temple in Hanoi, Vietnam, there were 3 diamond pegs mounted on a plate. In one of the 3 pegs, 64 golden discs with a hole in the middle were stacked on top of one another in the order of its size, with the largest disc on the bottom and the smallest one on top. The monks at the temple moved the discs one at a time day and night. The legend states that the world would come to an end when all 64 discs are moved to one of the empty diamond pegs. There were 2 rules to follow when moving the discs. First, only one disc can be moved at a time. Second, larger discs cannot be placed on top of smaller ones. Simply put, the legend tells that the world will end if all the 64 discs are moved to another peg while following these 2 rules. How much time do we have until the world comes to an end? We have to move the discs at least 2 to the power of 64 minus 1 times to relocate 64 discs to another peg following the 2 rules. When we calculate this number, we get a number that is almost too large to read. 2 to the power of 64 minus 1 equals 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709 million, 551,615. Moreover, this is the minimum number of moves required, meaning that the monks make no mistakes at all. How long will it take to move 64 discs? Let us suppose that it takes 1 second when the monks move one disc and calculate the time. First, attach the unit of time. Second, to the minimum number of moves required. By converting this to minutes, to hours, to days, to months, and to years, we get 584.9 billion years. In short, we still have quite a lot of time left until the end of the world. As we already know, the universe is about 13.7 billion years old. Besides, the age of the Earth is about 4.5 billion years, which is much shorter than the time it supposedly takes to reach the end of the world. In conclusion, we still have much time left because it would take at least 584.9 billion years to move all the 64 disks in the legend of the Tower of Hanoi, should we successfully do so without making any mistakes. Now let's return to the Fibonacci sequence. Even today, we use the Fibonacci sequence frequently because of many reasons. From the perspective of simple calculation, understanding the sequence is not difficult at all. The Fibonacci sequence goes as follows: 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and 3 plus 5 is 8. This regular sequence of these numbers appears surprisingly often in nature around us. As mentioned earlier, the number of petals flowers have is a typical example of the Fibonacci sequence. The number of seeds of sunflowers or the shape of pieces of pineapple skin also follow the Fibonacci sequence. The range of places we can find the Fibonacci sequence is beyond our imagination. Let us examine an interesting case of square numbers. Take a look at the first few numbers of the Fibonacci sequence. The square of 1 is 1, the square of 2 is 4, the square of 3 is 9, the square of 5 is 25, and it goes on and on. As we already know, in the Fibonacci sequence, we can get the next number by adding up two preceding numbers. What kind of regularities can we find if we get square numbers of each number in the Fibonacci sequence and add two neighboring square numbers? We can discover a new numeral sequence that goes as follows: 1 plus 1 is 2, 1 plus 4 is 5, 4 plus 9 is 13, 9 plus 25 is 34, and so on. In addition, what would happen if we kept adding up all the numbers from the first to the final number in the Fibonacci sequence as shown in the figure on the right? 1 plus 1 plus 4 is 6. Add another 9 to get 15, add 25 to get 40, and add 64 to get 104. This is not the sequence of numbers we usually find in the Fibonacci sequence. However, we discover that the Fibonacci sequence is hidden in this sequence upon a closer look. The number 6 is the product of 2 and 3, 15 is the product of 3 and 5, and 40 is the product of 5 and 8. As such, we can find the numbers like 2, 3, 5, 8, etc., in the Fibonacci sequence when we express the sum of numbers as a product of two numbers. It would be very interesting to figure out why this rule exists. Let us first see why the sum of the squares of 1, 1, 2, 3, 5 becomes the product of 8 and 13. The figure on the right would help us to understand this. Attach a square with a side of 1 next to another square of the same size, and we get a rectangle surrounded by the sides of 1 and 2. Attach a square with sides of 2 below the rectangle, and attach a square with sides of 3, another square with the side of 5 below, and a rectangle the size of 8 on the side. We end up with a large rectangle. What would be the area of this large rectangle? If we add all the areas of squares in the rectangle together, we can get its area. In other words, the area of the rectangle equals 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared plus 8 squared equals 104. In addition, we can also get the area by multiplying the length and height because we have a rectangle. The height of this rectangle is 8 and the width is 5 plus 8 equals 13. Thus, the area of the rectangle is 8 multiplied by 13 equals 104. Because we calculate the area of the same shape in two different ways, the sum of square numbers of 1, 1, 2, 3, 5, and 8 and the product of 8 and 13 are equal to each other. If we keep using this method, we would get rectangles made up of two neighboring numbers in a Fibonacci sequence, a rectangle with sides of 13 and 21, a rectangle with sides of 21 and 34, a rectangle with sides of 34 and 55, a rectangle with sides of 55 and 89, and so on. Let us try to divide the length by the width of the rectangle. 13 divided by 8 equals 1.625, 21 divided by 13 equals 1.6153, 34 divided by 21 equals 1.6190, 55 divided by 34 equals 1.6176, 89 divided by 55 equals 1.6181, etc. We can see that if we divide the larger of the two neighboring numbers in a Fibonacci sequence by the smaller one, we get closer and closer to the golden ratio. The golden ratio hidden in nature was first discovered by the Pythagorean school and was first defined in mathematical terms by Euclid. The golden ratio is still widely used throughout our daily lives today. Suppose that a girl plans to give a birthday gift to her friend. She buys the friend's favorite candies along with a box and ribbon to wrap the gift. She wants to put the candies in the box and tie the ribbon around it. Where should she tie a ribbon to make the gift look the nicest? The box looks rectangular from above. Assuming that she ties a ribbon to the top of the box, the ribbon would look the nicest if the ribbon is located according to the golden ratio. Of course, based on personal preference, some people may prefer to tie the ribbon across the center of the gift box. Still, the ancient Greeks were particularly fond of the golden ratio. Whenever they divided a line segment into two parts, they always thought about the most beautiful ratio. When we divide a line segment into two parts based on a point, we get a long and a short line. The Greeks were aware the most beautiful way to divide this would be according to the following ratio: the length of the shorter line, 2, the length of the longer line, equals the length of the longer line, 2, the length of the entire line. If the entire length of a line segment is x and the length of a long line is 1, the length of a short line is x minus 1. This gives us the proportional expression of x minus 1 to 1 equals 1 to x. We can also get a quadratic equation in the form of x minus 1 times x equals 1 by multiplying the inner terms together and the outer terms together on each side of the equation. When we solve this equation for x, we can get the golden ratio, which is x equals 1.618. Polygons come in various shapes: isosceles triangles, regular triangles, trapezoids, parallelograms, rectangles, rhombuses, squares, and regular pentagons are just a few examples. What is the shape of polygon that you think most beautiful? The polygons that have the golden ratio is called golden polygons. Is there really a golden polygon? The Greeks liked the golden polygons because they thought that the golden polygons were stable and harmonious. They found the golden ratio in the regular pentagon consisting of 5 sides of the same length. They drew 5 diagonal lines from each vertex of the regular pentagon. In this process, they discovered that these 5 diagonal lines divided each other into the golden sections. Through this golden division, a smaller regular pentagon is created in the center of the original regular pentagon. If we draw 5 diagonal lines again in this small regular pentagon, another smaller regular pentagon will be created. We can continue to use this method to endlessly create smaller pentagons within a pentagon. The fractal structure that has endless identical shapes within itself has the golden ratio. Where can we utilize the secrets of the series of numbers found in nature? Pythagoras, a Greek mathematician, believed that numbers were the origin of all things. Therefore, he tried to express everything with numbers. Pythagoras came up with a ratio that all people feel is the most beautiful. That is why the Pythagoreans used the pentagram, which contains the golden ratio, as their symbol. Pythagoras, who argued that the essence of beauty is in proportion, order, and harmony, believed that the golden ratio was the most stable and balanced ratio of nature. The Fibonacci sequence also contains the golden ratio. As the adjacent numbers in the sequence become larger, the ratio between the numbers become closer to the golden ratio. As is the case with the Fibonacci sequence, the golden ratio is a mysterious regularity of numbers found in nature. The golden ratio, which presents beauty and harmony, is not only be found in architecture and artworks, but also in our daily lives. We feel a sense of beauty, harmony, and comfort when looking at the Parthenon in Athens, Venus de Milo, and Mona Lisa by Leonardo da Vinci because they contain the golden ratio. The proportions of credit cards, business cards, and postcards are all made to be close to the golden ratio. Also, because the golden ratio is known to be a beautiful ratio that eases our eyes, the proportions of the length and width of books, television screens, and movie screens are all made to be close to the golden ratio. The grid system is used to use a screen or paper efficiently. It divides the screen or paper into consistent sections. Simply put, we may think of it as proportions used to make photographs and drawings pleasing to look at. Take a television screen as an example. When directors film a person, they make sure there is some space above the person's head on the television screen. This space is called the headroom. The headroom is used for most compositions on the screen to place the subjects more naturally. If a person's face filled up the screen completely, it would be quite overwhelming and discomforting to the audience. Today, there are not only many channels available but also an abundance of information about them. This means that captions need to be inserted to provide information such as the program schedule or additional explanation about the visual material. More information, such as the broadcaster logo, clock, and the program name has to show up in the upper left and right corners of the screen. If such information were to be placed on screen without any set of rules, it would be frustrating to the audience. So, the screen has structured and arranged so that the audience can take in the information easily. Grid design determines how to divide the screen and how to arrange it. This technique is also full of the golden ratio, the harmonious law found in nature.